Hello everybody, I hope you are ready to endure my shitty French accent for 35 minutes. Good luck. So my talk today, this is the first time I'm doing that talk, and I will also introduce to you a new tool. I will see later. I hope the demo will be fine. Let's cross the fingers and praise the gods of demos. So my talk today is how to dissect a malware by collecting its syscalls. I will explain what syscalls means. I don't really explain what malwares are. I think everybody knows. I will also explain what eBPF is, why it's a game changer. So who am I? In French, Thomas Labarussias. Currently, I'm senior developer advocate at Sysdig, a Californian-based cybersecurity company. I'm senior developer advocate for them. I'm not managing the commercial product. I'm totally dedicated to the open source projects we developed. I was SRE for almost 10 years. I did 5 years of on-call. For example, I also did some FinOps because just to learn. I'm CNCF ambassador for almost a year now. Falco contributor, we'll see later what Falco is if you don't know the tool. Creator of tools for Falco. Beer geek, I drink a lot of beer, too much. And you can find me out on these social networks. So, on the other side, I'm not what we can call an hacker. I'm not an expert in malware analysis. I'm not white hat or even worse, black hat. So just to explain everything I will show to you now, you can reproduce it quite easily. You can understand quite easily what I will present, how it works, and what you can do with. You don't have to be an expert in kernel, in eBPF or else. Just for everybody, for example, for people that call them DevOps, what syscalls are. Syscalls are for system calls. Basically, when an application needs to get access to, for example, memory, to some CPU cycles, to the file system, or anything else, it will ask the kernel in Linux. Don't talk about Windows world, we don't care about that. But for Linux world, or Unix, each time an application needs something from a physical hardware, or not, or logical, it will ask the kernel the access. The kernel will say, okay, you have access, you don't have access. Wait a few milliseconds because someone else is dealing with that stuff, a mutex, for example. This, you can basically imagine the system calls as the API to access to the functions of the kernel. If you are familiar with this complicated stuff called the glibc, or if you are in the helping world muscle, you can consider them as SDK to manage the API, which is the system call. Oh, I have a clicker, I forgot that. In the last years, the kernel maintainers introduced eBPF for extended Berkeley packet filter. It comes from the BSD world, thanks to them. Basically, it's a way to introduce inside the kernel new features, new functionalities, without any modification of the kernel. It's live, it's dynamic. It comes with a lot of control, a lot of verifications to be sure we not create a mess in the kernel. It's really funny and nice to use. Right now it's used for security, Sysdig, Falco. It's also used for network, for example, Cilium. I saw the t-shirt. And diagnostic, a lot of stuff. So how it works, basically you write your program with Go, Rust. I think Python has also SDK. It will create an eBPF program. This program will be checked with a verifier by the kernel. It will be, to be sure you will not introduce memory leak, infinite loop, bad stuff. If the verifier agrees about your code, it will transpile them into bytecode for the kernel, and then the kernel will run in a little sandbox your piece of code. You can attach your eBPF, what we call a probe, to some hooks. Basically, each time the kernel needs to, for example, trigger a syscall or listen for a syscall, it will call your probe and do some stuff. This is how, for example, Cilium intercepts the network's packets to manage the routing, for example. And this is how sysdig or else are collecting the syscall to do what we'll see later. I think it's pretty clear or not. Get an eye on eBPF.io to know more about eBPF. I will not explain that in a lot of details, but this is basically the main idea. How to analyze malware? We have two global methods. The first one is to do static analysis. Like you get the binary, you open it in Vim, you change the mode for hexadecimal, and you try to see what's inside the binary. You can also try to decompile, uncompile the binary to get back the original code base, all this stuff. I'm not a security expert, or at least not for that part, so I will not do that. I prefer the dynamic analysis. Basically, the main idea is to, we have a malware, let's run it and see what's happening. It's not a new thing. I'm not introducing you a new method to do analysis of malwares, but I will present you maybe new tools for you to do so. We'll use, of course, eBPF. It's in my title. First, to do so, we'll use sysdig. I don't know if you know the company already, but it has been founded on top of that tool, also created by the company. Sysdig, you can consider that like a Swiss Army knife, including trace, TCP dump, htop. If a lot of different tools we may already use to do diagnostics or to analyze our systems. You can see that like we put all together into a single tool. This extract, this snippet is basically what we can get from sysdig from start without any more actions. If you're familiar with strace, it's basically the same pattern, but we can do much more. To use eBPF with sysdig, you have to just add this little flag. Why? Because sysdig has been created way before eBPF was introduced in the kernel. So by default, till now, sysdig will try to use a kernel module. We provide the kernel module, of course. But if you want to use eBPF, just add this flag. So we can add to our commands understandable and human understandable filters. It's a way to just capture a subset of the syscalls, not all of them, because so many things are happening in your systems at any time. It's easier to filter and focus the scope on only few syscalls. I think even if you're not familiar with syscall, if you never tried it, you are able to read the filters right now. I will focus on the container named, in that case, sandbox, on the Python program, and I will only consider input-output, basically read or write from a file, from a socket, network or Unix. And in that case, I will only consider file descriptors which are IPv4, so basically I will just consider network I/O. Easy to read, easy to understand. This is basically with that command, you will see exactly what we had in that snippet. But sysdig introduces what we call chisels. Chisels are the way to basically format the output to get more, to get nice visualization of the syscalls. For example, with the exact command before, if I'm scoped to the network I/O for the program Python, yes, inside the container named sandbox, and I use the chisel echo FDS, I can get that view quite easily. If you're familiar with TCP dump, you know we can collect the HTTP packets And then with a complicated command, we can have the input and output. With just that command, you can have the exact same in a much, much easier way. And we also provide a terminal user interface if you want. If you're not really familiar with the filters and the chisels, you can use the TUI. I will try to show you sysdig in live. Cross fingers. Okay. Is that big enough or not? Oh yeah. So I will run this small Python server. I can curl it, pretty easy. And we'll try to get the output of this Python server like I did for the slide. So basically, I will curl my server, and I'm scoped on IPv4 on the container name Python, and I'm using that chisel to extract in real time the packets. It worked, nice. So from the Python perspective, we have the read. So basically, what the Python server received from my curl call. So we have the HTTP method, the host, user agent, my homemade header, the source IP, source port, and the destination IP, which is the IP of my container, and the port. And we also have the right for the headers and for the content of my beautiful HTML page. I can show you another example, much funnier if you want. I think you are also familiar with top, basically a way to monitor your system. So basically, I will run top every 1 second. And if you know how top works, basically it reads under /proc to get statistics. So basically, one line on that graph is 1 second. Each colored bar means we have events. Green means we have a few events. Red means we have a lot of events. In that situation, we see every 1 second, top will read from /proc, and you have these, we call that spectrogram. We can do so with almost anything. So, for example, if you focused on DNS requests, you can use that graph to see visually if you have a lot of DNS requests or not. Another nice thing with sysdig is, like TCP dump, you can do capture. And you can apply the same chisel, the same filters, like we do, like we can do with TCP dump. Let's go back. To run my malwares, I will do that with a simple sandbox, because I don't know if you watch the movie with James Bond, I think. Basically, it runs malware directly in the lab. You see what I mean if you watch the movie. And I will not spoil, but I think you see what I mean. So we'll use a trashable sandbox. I'm pretty lazy, so I did it manually, but you can do that with Vagrant, Terraform, CDK, Pulumi, whatever. In my situation, I use the basic EC2 instance in Amazon, and I'm running two Docker containers in that EC2 instance. One for sysdig, one for the malware. We'll see why. And to be sure to not be a noisy neighbor, I also blocked all outbound connections to avoid the malware to try to replicate or to cause something else, or if it's a botnet, or I don't know, I don't want to be a pain for the other. But you could just open, for example, DNS port why I choose to use a VM and Docker. So for the VM, because it's depossable, easy to reproduce, easy control for the inbound, outbound collections. I don't have to write any IP tables. Just with a security group in Amazon, it's easier. And for Docker, it's even more easy to trash them and reproduce them. And so we have one level more of sandboxing, easy to switch from one OS to another. For example, if my malware was supposed to run in Red Hat environment, I can use a Red Hat image. If it's Ubuntu, I can use a Ubuntu image and so on. Easy to install new packages in my Docker image or directly in the Docker container. And it's easier to install sysdig aside. And with that, because I have another level of sandboxing, I can just filter the syscalls concerning that container, including the malware and not the whole system. It allows to get smaller captures and at least with only suspicious events. How did I collect malwares? Just open anyone to internet and it's enough. But in that situation, my company ran an honeypot for a few weeks. You have the whole story there. I will provide to you slides if you want. All links are clickable. So we ran a malware, an honeypot, and we were able to collect malwares. You can also try to search for them on GitHub. Some people are providing zoo of malwares on GitHub. You can use them if you want. So after a few days, we collected few malwares. So I asked them to send them out to me. And how we will explore these captures. Maybe you don't know this guy. Well, basically, he pays my salary because he's my boss. He's Loris Journey. He's CTO and founder of sysdig. He was the original creator of sysdig and Falco. And he also co-created a small tool, maybe you know it, Wireshark. I think you know Wireshark. Pretty common in the network administrator world and sysadmins too. It's a nice piece of software to basically explore a TCP dump, network packet capture. So Wireshark is now part of sysdig. It's still a foundation, but it's part of sysdig more or less. And the developers of Wireshark are currently developing a fork of Wireshark called LogRay. I don't know if the name is temporary or not, but let's call it LogRay. This is a new version of Wireshark able to read sysdig captures, able to read syscall packet capture. And this is the first time someone will do a demo of that tool, so it might crash because it's still an alpha, and basically it might crash. So I did some captures. I ran some malwares they gave me, and I will not dig too much. It's not the topic today, but I will show you some classical patterns we can find inside malwares if it works. Sorry. Spoiler. So, big enough. I'm sorry, there is an issue with Qt. It doesn't want to change to light theme, so it will be in dark mode for now. I'm very sorry for that. So let's try the untitled. So we see a global capture, so it was really short, few minutes, 1 or 2 seconds of capture. All these syscalls happened. We have, for example, readwise. So this program called untitled wrote a lot of stuff, read a lot of stuff from TCP, network connect TCP, but it's not really important. Basically, it just printed in the standard out hello world. I don't know why exactly. But if you notice that, it forked before to create a program called var-Sophia. var-Sophia is basically a crypto miner, I think. Basically, with just that, with the name of the processes, you can easily find out what malware it is. But this is not the part which is funny. This part is funny. After I ran that malware, it deleted itself. Unlink is syscall from the kernel to basically delete. It's not really a deletion, but to unleak a process. And you can see it deleted itself at the end. Classic to add your other capture. This one is funny too. Right. This one will add itself in the /etc/lc.local. So basically, to be sure it will run even after reboot, it adds itself in the init process, in the list of process to init. Pretty classical. This is a crypto miner, for example. Another one, Sakura, not so much things to show in that one. We can see the DNS request. No success because all connections were blocked, but we can, if a process is trying to reach an external DNS for particular domains, for example, you can get that packet. Another one. Oh, this one is funny. Let's find read write. This one I knew before. It's a crypto miner. So basically, it will encrypt a whole folder. Then a message will be printed, will be created with that content, with a Tor onion address to reach the hackers, the hackers, to contact them, to pay, to encrypt, decrypt the files. The funny thing is, if you take a look about the network, no network activity from the malware. It means basically either they are lying, so they don't have any key to decrypt your files, either the same key is used to encrypt all files for all victims. So if we're able to find that key, we're able to decrypt all files for all victims. I'm not so sure, but and the name of this malware you can search on Google after is Comty. And maybe another one. Sucker. Don't remember which one I did, and title. Oh, this one is not really interesting, but oh, demo effect, you see? Oh, better. We see the gym. Okay, I think I have an issue now. Now let's find another one. This is exactly what I did in my demo with sysdig, just to prove we can record a capture and read it with logray/wireshark, and you have all message. And if I follow the stream, you can see the exact same read and write we had in the terminal before. So we thought with sysdig, we can create easy to read, easy to reproduce captures. It's funny, you can do that on the fly, in your command line, in your terminal. But if you want something running in the background using the same filters, able to, for example, spot the encryptions, spot suspicious DNS requests, you can use Falco. Basically, Falco and sysdig share the same libraries, the same code base. Just Falco is a daemon to do that in the background. It's a graduated CNCF project since a few months now, powered by eBPF too. So if you're able to run sysdig and write some filters for sysdig, you're able to write some rules for Falco. And you can also create a capture with sysdig, pass it to Falco to test your rules. I think I'm okay. If you have any question, I'm open to answer. I will provide to you the malwares if you want to repeat what I did. And if you want to reproduce with LogRay, reach me. I will get you in touch with the developers because building that on Arch Linux was not so easy. Thanks.